Right, so now that was DNA memory. Now we're going to hear about DNA computation from Ross King from Manchester.
Okay, thank you very much. What I'm going to talk about is DNA supremacy. So what I'm aiming to do is something very ambitious because, of course, electronic computers are probably the best technology since agriculture or fire or something. You know, it's a fantastic technology. But I'm aiming to build a DNA computer which can compute something which an electronic computer nor a quantum computer could actually compute. And I think we have a plausible pathway to do this, and the type of computational problem we intend to demonstrate this on is NP-complete problems. So these are the most important practical class of problems. So it's not some, if you look at what the quantum computing people are talking about as supremacy, some strange mathematical things which of little practical relevance. NP-complete problems are very important. Okay, and this is the most important slide of my talk. Since we're in the Isaac Newton Institute, theoretical computer science, i.e. mathematics, is very, very clear about how to make a fundamentally faster computer. You don't increase the clock speed, you don't put more processors on the chip, you don't even build a quantum computer. What you do, according to theory, is build a non-deterministic universal Turing machine. Okay. That's what theory says. The question is, can you actually build such a thing? Okay. And that's what, through my talk, I'll try to explain what that means. So, universal Turing machine is what Alan Turing, his greatest, on Grantchester Meadow had this, God touched him and he had this idea of the universal Turing machine. And the key point about the universal Turing machine is that this is all you really need. You can't build a more fundamentally more powerful computer which can compute something a universal Turing machine can't. And people have tried and no one's ever succeeded. Something to do with the laws of physics, probably. Yes, and so given that you're going to build a universal Turing machine which can compute anything which another computer can compute, it comes down to speed. So some computers are faster than others, and some problems are more difficult to solve than others. And in computer science theory, there's basically two main classes: the exponential ones, which we don't think any computer can solve, and the ones which are polynomial, which electronic computers can solve pretty efficiently. And there's these problems in the middle called the NP-complete ones, or the NP problems. So it's the most important class in computer science and complexity theory. Informally, the basic idea is that in this class, if the computer is given the solution to the problem, it can check that solution efficiently in polynomial time. But we don't know of any way to find, using a computer, that solution anything short of exponential time. Okay, so there's this dichotomy between checking the answer and finding the answer. And NP-complete problems are the most difficult ones in this class. So if you can solve them, you can solve all the other problems in that class. This concept of NP-complete problems was discovered in the West in the 70s. It was also independently discovered in the Soviet Union, in Novosibirsk. They call these problems Peribor problems. And basically, the key insight is that there is no way to solve these problems apart from brute force. You've got to check every possible potential solution. That's the basic idea. There is no quick solution to these problems. Yeah? The only approach is brute force, and that's our motivation. If it's going to be brute force, let's make a brute force computer. And basically, from the physics, or the theoretical side of things, the NP class is the class you can solve using only local interactions. So if you imagine a computer which can do forks, but can do no long-range communications, you can solve NP-complete problems with such a computer. Okay. Oh, and there is this problem, P equals NP problem. I think it's the most important in mathematics. It's certainly most important in theoretical computer science. I'm working on the basis that P doesn't equal NP. If it did, it would transform the world. Mathematics would be basically solved, and all sorts of world transforming things would happen, like internet security would disappear. But and it would be actually very easy to prove that P equals NP. All you have to do is find NP problem, which you can solve in P time, and you've NP complete problem, and you've done it. The fact that no one's done that tends to imply that P doesn't equal NP, but who knows? Okay, what's a non-deterministic universal Turing machine? An old-fashioned but insightful way to define the concept of NP problems is through the concept of a non-deterministic universal Turing machine. Basically, these are the problems which a non-deterministic universal Turing machine can solve in P time, in polynomial time. So in a standard computer it's deterministic, from any given state it can only go to an x given state. There's only one possible state. The difference of a non-deterministic universal Turing machine is that there's n possible states from any one state. Okay, that's the basic idea. It can go to one of these n states. And if you read the theoretical computer science textbook, basically they say such a machine is impossible to build. Their ontology is basically that the machine will guess the correct answer. You know, of these n possible next states, which one is correct, it will guess correctly which one is correct. And that is clearly something impossible to build. You know, you can't build such a lucky machine. That's why they're called magical, hypothetical, fictitious, etc. Our insight is that there's another possible ontology, and that is replication. At each choice point, what you can do is make the computer split into n parts and follow all possible n ways down the tree. Okay, so you're going to, instead of having one computer, you're going to have n computers, then n computers, etc. Okay, and that opens up the possibility of physical implementation. So this is the basic idea. You have one Turing machine. There's a choice point that splits into two Turing machines. Each one has choice points, etc. So you're going to build a tree of machines until what's called that's the accepting state, which is basically the halting state in the Turing machine. You found the answer down one of the pathways. Okay. Okay. So we want to implement this, and we want to implement it in molecular DNA, because to me, the most exciting thing DNA does is not store information, it's replicative. You know, DNA can replicate, and that's the insight. We're going to build the computers which replicate. Okay, we're going to do this not using the traditional Turing machine, but a thing called a TUI system. And a TUI system has equal power to a Turing machine. Okay, and it's a rewrite system. So basically, you have collections of rules of the form W to U in our words in some finite alphabet, and you see the string V prime, then you can convert that to VU V prime. Okay, so you're seeing a particular string of letters, a word, and you're rewriting it as another word. So it's a rewrite system. And it was proved very early on, actually, back in the 40s, or even earlier by Post, that any Turing machine can be rewritten as a TUI system and vice versa. Okay, and this is a universal TUI system. So if you see the pattern AC, you can rewrite it as CA. You see the pattern AD, write it as DA. If you see CE, you can rewrite it as ECA, etc. So these are reversible rewrite rules. And amazingly enough, these 7 rules are sufficient to compute anything. These are universal, so you can program anything, any possible computation can be programmed using these 7 rewrite rules. Hard to believe, but true. Okay. So this would, a program would be a particular pattern of these 5 letters. You see there's 5 letters here, A, B, C, D, and E. And the program would consist of rewriting these rules and rewriting them until you see a particular pattern of letters, the accepting state, which here is a sequence of the letter E at the bottom. So that's the basic idea. We're going to build this molecular rewriting system. And we're not claiming to solve the P equals NP problem or anything. We're going to build a computer which is going to get exponentially faster, but it's also going to take up exponentially more space. So that's the price we're paying. So we're basically going to try and trade space for time. Okay. So given NUTM is it gets exponentially faster, but also unfortunately takes up exponentially more amounts of space. So you eventually run out of space. Okay, because we're going to run out of space, we want to make the computers as small as possible. In fact, they're going to be individual strands of DNA. And well, a lot of this was said in the previous talk, but on a benchtop DNA computer, at least in principle, could execute something like 10 to the 20 operations a second. It could use very little energy, many orders of magnitude more than standard electronics. And we heard the previous talk about the density of information. How are we going to build one? So we're going to do this in DNA. Okay, this is a bit redundant. Okay, so the initial state of the start date is going to be a sequence of DNA. And we heard in the previous talk that it's actually, you can just print out that, you put in a ASCII file and you send it off to a company and they send it back the next day, the particular sequence you're interested, as long as it's not too large. During the program execution, all 7 rewrite states will be done in parallel with no fixed order, and all possible combinations will be executed. So that's important because there's no fixed order. You don't have to do one thing before another thing. You don't need to do one rule before another rule or do this rule or that. And that makes it much easier to implement at the molecular level because trying to get molecular systems to do things in order is very, very hard. The different DNA sequences just correspond to different possible computation states. An execution will halt when a particular sequence is produced. That's the halting state, or it's going to be encoded up in DNA. We had a very good tutorial on that in the previous talk, how to do that. There are different constraints when you want to do this in DNA than in storage. So we have an arbitrary way of writing programs. There's machines that can do that. You can buy these machines. We have to have a way of finding the acceptance state. And with the molecular biology, there's exquisitely sensitive ways of detecting particular sequences of DNA. So that's you're going to fish out the particular answer from your bath of DNA sequences. In the past, we've been using sequencing, but other approaches are possible. In fact, sequencing is very good because after all you have to do is get the answer into the top million possible answers, and the machine can actually find it for you. I'm going to do this with microfluidics to implement different rules in a practical computer. We physically implemented all these 7 rewrite rules in DNA with what's called site-directed mutagenesis technology, and that was basically took a year of messing about in the wet biology lab to get to work. There's 2 parts to that. Recognition, first you want to find all possible string rewrite positions in a theory rule, and then the actual rewrite part. So we had to split the thing up, and it was actually quite complicated in the end. You had to use ideas like microprocessing and things like that, microprogramming. But the basis of it all is basically Boltzmann's distribution. This is what says that it's physically possible to do this. This is what makes our bodies work as well. Basically it says energetically unfavorable states are probabilistically of low probability. So that when molecular systems bind together, the stronger that binding, or the weaker that binding, the less likely that is to happen. So we want to make things which you want to happen have strong binding, and things you don't want to have weak binding. And Boltzmann's distribution says that is actually physically possible. And we did a lot of work calculating all the numbers to show that a computer is physically possible. As I say, we did a lot of work in the wet lab to try to implement these. Well, we actually did implement these. The hardest ones to implement are insertions and deletions to order, because that takes, it's much harder to actually put something into DNA and to pull it out than just to change a base type. And of course, the biggest problem is noise. You know, in the early days of electronic computers, this was thought to be a fundamental problem, and von Neumann did a lot of work on error correcting computers with electronic components. But nowadays, electronic components are incredibly reliable. But noise is the fundamental problem with, say, quantum computing, and it's also a problem with DNA computing. But in DNA computing, at least this noise is classical noise, and we have good theory of how to deal with that. There are ways of using molecular biology to eliminate sequences that don't encode symbols, so syntactically incorrect ones. We can use error-correcting codes, like in the previous talk. We can do things in parallel without losing the exponential speedup. And the beauty of NP-complete problems is that if you actually find the correct answer, you can check that efficiently on an electronic computer. So if you manage to sequence the correct answer, you can recognize that efficiently. Okay, so what we're doing at the moment is something a bit different in that, so we've proved that we can build a non-deterministic universal Turing machine. Now we're actually wanting to build a specialized DNA computer to do NP-complete problems. These problems play to the strengths of DNA computers. The original work on DNA computing was actually on NP-complete problems by Elderman back in the early 90s. The problem, of course, and the hard part is to find an NP-complete problem which you can actually naturally implement using DNA. And we think we have found one of these. This nice. If you look on the literature, there's literally hundreds of NP-complete problems, but we found one which we think we can implement efficiently in DNA, and we think we know how to do the molecular editing more efficiently than using site-directed mutagenesis. And we hope to have funding very soon, and we have a patent application on this, so I'm not really allowed to say much more. I just want to finish off by saying a few things. So we solve NP-complete problems in a brute force way, but I think I'm arguing that there is no other way. That's what NP-complete problem is. There is no general approach to these problems apart from brute force. That's what P doesn't equal NP means. The process resembles an explosion. You know, it's like you're making more and more computers as you're computing away. And although DNA is very small, they're still of finite size, and this limits what you can compute and what you can't compute. So I'm told that the observable universe is only 10 to the 82 atoms, which limits our computer's volume. And actually, it turns out, according to the physicists, that the amount of computation you can do within a fixed volume scales by surface area rather than by volume, which seems non-intuitive to me, but it's to do with black holes and things like that. Most effort on non-standard computation is focused on quantum computers. Every time I open up Nature or Science, there's another paper on some physics of quantum computers. There does not yet exist a universal quantum computer. There's some theoretical computer scientists think quantum computers are actually physically impossible, or perhaps because it requires quantum laws to be accurate to too many decimal places for a start. We shall see. What is interesting is that what a non-deterministic universal Turing machine and what a quantum computer can do seem to be orthogonal. They both use non-determinism in a sense, but the quantum computer has this great advantage of not using up physical space, which is fantastic. But there do seem to be quite strict limitations of what a quantum computer can do. No one's really sure, but most people think they can't solve NP-complete problems. That seems to be beyond what a quantum computer can do, but we're not really sure. So I want to close. So a non-deterministic universal Turing machine is a new computational paradigm. I believe there's a plausible technological path to achieving DNA supremacy. So NP-complete problems which no electronic computer or quantum computer can solve. And as I say, yes, so the NP-complete problems are going to be where we're going to demonstrate supremacy. And I'd like to thank my collaborators, Constantine in Manchester, the other collaborators in Manchester, and our Indian collaborators. Thank you for your attention.
We have time for a few questions before we go out and find lunch. Please.
You did not talk about the cost. So what needs to be done to build this, and how much this is going to cost? Can you also make projections, or if it costs X amount of today and 10 years?
What to actually, for the development work or the
build this machine?
Oh, to have to. Well, that's I don't know. I would say tens of millions to build a DNA computer which has supremacy, and that compares to the many billions which have already been spent on quantum computers. So I don't think it's hundreds of millions.
But how is it going to scale? Is it going to scale down in terms of the cost in next 10, 20 years?
Well, actually, to build a machine would cost very little, because it's, you know, what's there. It's some DNA, it's some microfluidic pumps. That's all there is. It's going to use a few kilowatts of power at most. It's not going to be very much.
With regards to your mystery problem, I realise you don't want to say anything about the actual nature of the problem, but what sort of problem instance size can be currently solved using classical machines, and where do you think the supremacy crossover will happen in terms of the size of the instances that you can?
For this particular problem, because it scales, as you know, exponentially, so the 4-size problem I can't solve by hand. Well, I probably could if I spent a few days at it. You know, my estimate for supremacy is 22-size problem.
Okay, so there's the supremacy where it crosses over, and it's supreme beyond that point of the size of the problem. How much further can you go until you've used up all the matter in the universe solving your problem? So how many orders of magnitude do you actually get where you've got the supremacy?
So I say supremacy is on desktop, so I don't know how many desktops you get in the universe.
No, I'm not talking
that's
about...
the question.
No, I mean, because in order to solve the problem, as you said, you need an exponentially larger amount of DNA for each increase in the size of...
Yeah, that's why I'm saying you need to scale up the desktop. To make one that's 10 times more powerful, you need 10 times desktops, don't you? So it's just volume. So how many volumes you get in the universe?
Not that many orders of magnitude before you're off the planet.
Yeah, I think there's quite a few desktops on the planet, but it's I don't know, to scale up to the size of these new the supercomputers, the physical ones you see now. There's probably 1,000 of them or something, or 10,000 like that. Yeah.
Steve?
So at the end of the computation, there are, if I understood correctly, 2 to the n DNA sequences in this soup, and you're looking for one of them.
Yes.
So how hard is it to retrieve that one from this soup?
That comes down to Boltzmann's law. Yeah. So you can. So you want to be able to find it. Yeah. So you're going to have almost equal numbers of sequences looking for it. That's the plan. Okay. So that just doubles the amount of volume you need, and it comes down to whether that binding between the answer and what you're looking for is strong enough to outweigh all other ones. And that's an exponential because of Boltzmann equation. And as I also said, if we can get it down to the top million or so, then that's all we need, because sequencing can then find it. So if you manage to fish out the top million most likely ones, and then sequencing already is fast enough to do that for you.
You said that we are effectively trading time for space, but there should be something about time here. So is it time just waiting until we run out of the resources? And if we got something, we are lucky. If not, we aren't.
Yes, well,
Resources.
well, that is the problem with
energy. Since you refer to Boltzmann, it's all about energy.
yeah. Okay, so you're not asking about how fast the actual DNA is computing at sort of at best 1,000 operations a second or something like that. But we have 10 to the, I don't know, 20 of them or something like that. A large number of them. Yes, you just wait until you find the solution. If there is no solution there, which is possible in NP-complete problems, then you're looking for the opposite type of, then you won't find it if there's no solution. Yeah.
It seems like this phenomenon, sometimes characterized in the literature before, is like prodigality. It's kind of it's instead of frugality, it's prodigality, relying on the fact that Mother Nature explores all possible ways concurrently until it basically runs out of the resource. So because nature is not interested in saving energy, nature is interested in prodigality, effectively just finding the maximum for what it has.
Well, I'm not sure about nature, but what I'm arguing is that there is no other approach for NP-complete problems if P doesn't equal NP. You have to just check everything, and if you're going to check everything, you may as well do it your computer's going to be as small as possible and use as much space as you can. Yeah. That's the argument.
We have a question at the back.
Yeah, just going back to the previous question, what technique are you using to fish out the final result?
Currently, we're just using sequencing.
Okay.
But we could, fish out matching sequences. There's very interesting technical computer science problems of programming things like TUI systems. We don't really know how to do that. We know in principle that you can make it say this is I'm the answer. You fish out the answer, then you sequence the rest of the information to get the answer.
The problem might be if you use something like PCR. The problem might be that PCR is limited to a specific length, which then limits the size of your solution space, right? Maybe there's other methods for it.
Well, I don't think that from energy type arguments, I don't think the answer has to be that big. It's like PCR should deal with it, I think.
I'm sensing the energy levels going down a little. We should be ready for lunch, I think, feed our brains, as we've been told we need to. So let's thank Ross again.